in the fiery crucible of Earth's earliest days. During the Hadean Eon spanning from about 4.6 to 4 billion years ago, the planet was a barren, infernal world. Born from the chaotic debris of the solar system's formation, Earth endured relentless bombardment by asteroids and comets. Its surface a molten sea of lava under a toxic atmosphere thick with volcanic gases and steam. Temperatures soared to thousands of degrees, and the crust was perpetually reforming amid cataclysmic impacts. No life could have taken root in this hellish environment. It was a sterile rock, devoid of oceans, stable land masses, or the chemical stability needed for organic molecules to persist. This eon, named after Hades, the Greek underworld, set the stage for our planet's transformation, as cooling processes gradually allowed for the formation of a solid crust and the accumulation of water from cometary deliveries, paving the way for habitability. Fast forward approximately 500 million years after the late heavy bombardment, a period of intense meteoritic pummeling around 4.1 to 3.8 billion years ago, and the first whispers of life emerge. By around 3.5 billion years ago, in the Archean Eon, evidence points to the existence of prokaryotic organisms, such as simple bacteria and cyanobacteria, often called blue-green algae. These microbes, discovered in ancient rock formations like the Pilbara Craton in Australia, left behind stromatolites' layered structures formed by their metabolic activities. These early life forms were anaerobic, thriving in oxygen-poor environments, and they harnessed chemical energy from hydrothermal vents or sunlight through primitive photosynthesis. This marked a pivotal shift. Cyanobacteria's oxygenic photosynthesis began oxygenating the atmosphere, setting off the Great Oxidation Event around 2.4 billion years ago, which dramatically altered Earth's chemistry and enabled more complex life to evolve. As we advance into the Proterozoic Eon, from 2.5 billion to 541 million years ago, the fossil record reveals the dawn of diverse and complex multicellular organisms. This era saw the rise of eukaryote cells with nuclei and organelles likely through endosymbiotic events where prokaryotes merged. By the late Proterozoic, around 600 million years ago, soft-bodied multicellular life, such as the Ediacaran biota, appeared in shallow seas, resembling fronds, discs, and quilted mats. These organisms, preserved in sites like the Ediacara Hills in Australia, represented early experiments in multicellularity, feeding on microbial mats or filtering nutrients from water. Environmental changes, including fluctuating oxygen levels and glaciations like snowball Earth episodes, challenged but ultimately spurred this diversification, laying the groundwork for the explosion of life that followed. The beginning of the Cambrian period, around 541 million years ago, heralded a revolutionary chapter in Earth's biological history, the Cambrian explosion. This rapid diversification saw the first organisms with hard shells and exoskeletons, providing protection and enabling new ecological niches. Fossils from the Burgess Shale in Canada showcase bizarre creatures like Opabinia and Hallucigenia, alongside early arthropods and chordates. Trilobites, those iconic armored scavengers with compound eyes, dominated the seas toward the end of the Cambrian, with over 600 genera identified in the fossil record. These mud-burrowing, segmented animals ranged from tiny to over 2 feet long, thriving in diverse marine environments. This burst of complexity, driven by rising oxygen, predation pressures, and genetic innovations, transformed ecosystems from simple microbial communities to intricate food webs. Yet, as life blossomed, extinction events loomed as inevitable counterforces, pruning the tree of life while fostering resilience. Nature has unleashed numerous mass extinctions, such as the Ordovician Silurian event 445 million years ago, which wiped out 85% of marine species due to glaciation, or the Permian-Triassic Great Dying 252 million years ago, eradicating 96% of marine life amid volcanic eruptions and climate upheaval. The Cretaceous-Paleogene extinction 66 million years ago, triggered by an asteroid impact in Chicxulub, Mexico, famously ended the reign of non-avian dinosaurs, paving the way for mammals to dominate. Despite these cataclysms, life has persistently rebounded, adapting through evolutionary innovations like flight, warm-bloodedness, and intelligence. As Jeff Goldblum's character in Jurassic Park quipped, "Life finds a way," echoing the tenacity seen in survivors like crocodiles and birds that endured the dinosaur apocalypse. Looking to the future, humanity faces cosmic threats that could echo these ancient extinctions, starting with near-Earth asteroids. In 2029, the asteroid 99,942 Apophis, nicknamed the God of Chaos, will make a remarkably close approach to Earth on April 13th, a Friday, no less. Measuring about 340 meters across, roughly the size of the Empire State Building, it will pass within approximately 32,000 kilometers of our surface, closer than geostationary satellites. While initial calculations raised alarms about potential impacts, refined orbits confirm no collision risk for 2029 or subsequent passes, though its trajectory could be slightly altered by Earth's gravity. As astrophysicist Neil deGrasse Tyson has emphasized, this event underscores the need for space programs to deflect such threats, lest we join the dinosaurs as cosmic laughingstocks for failing to act on our intelligence and technology. Beyond asteroids, the universe harbors even more exotic perils, such as gamma-ray bursts, GRBs, the most energetic explosions known, often resulting from collapsing massive stars or merging neutron stars in distant galaxies. These bursts release beams of gamma rays that, if directed at Earth from within a few thousand light years, could strip away our ozone layer, exposing life to lethal ultraviolet radiation from the sun. The result? Mass extinctions, acid rain, and disrupted food chains, as seen in hypothetical models linking past events like the Ordovician extinction to GRBs. Though rare, occurring about once per million years in a galaxy like ours, a direct hit would be catastrophic, ionizing the atmosphere and triggering global cooling or wildfires. More insidious still are rogue black holes, wandering stellar remnants untethered from stars or galactic centers. Estimates suggest the Milky Way contains around 100 million such black holes, formed from the deaths of massive stars. The odds of one intersecting our solar system are astronomically low, about 1 in a trillion, but the consequences would be apocalyptic. Even a primordial black hole smaller than Mercury, with a mass thousands of times Jupiter's, could disrupt planetary orbits through its immense gravity. As it approached Earth, tidal forces would trigger mega-earthquakes, volcanic eruptions, and atmospheric stripping, ultimately shredding the planet into a molten remnant or accretion disk. Perhaps the most terrifying doomsday scenario is vacuum decay, a theoretical quantum event rooted in the instability of our universe's vacuum state. According to quantum field theory, our reality might exist in a false vacuum, a metastable energy state higher than the true ground state. If quantum tunneling creates a bubble of true vacuum, it would expand at the speed of light, rewriting the laws of physics within. Particles would lose mass, forces would alter, and all matter would disintegrate. Stars, planets, and even atoms would cease to exist as we know them. The silver lining? Its light speed propagation means we'd never see it coming. No warning, just instantaneous oblivion. If cosmic fortune spares us these fates, one inevitability awaits: the sun's transformation into a red giant in about 5 billion years. As hydrogen fusion in its core dwindles, the sun will swell dramatically, its outer layers expanding to engulf Mercury and Venus, while Earth likely tidally locked and scorched may be vaporized or stripped of its atmosphere. This helium-burning phase will mark the end of Earth's 9 billion-year odyssey, from molten birth to a biosphere teeming with life, ultimately consumed by the star that nurtured it. In the grand cosmic narrative, Life's persistence amid such perils highlights its fragility and ingenuity, urging us to safeguard our fragile home against the indifferent vastness of space.